Okay, I foreshadowed a little bit at the end of the last video. The last complication you might run into if you need to find the volume of a solid of revolution is that it might not be the case that the region you're revolving is flush up against the axis you're revolving around. That means after you revolve around, if you imagine taking a slice, there's going to be a big hole in the middle of your slice. So if the slice is a cylinder, a very thin cylinder with a hole in the middle, we call that a washer. And we're going to need to know that the volume for a washer, pi big R squared, where R is the radius of the hole, W-H-O-L-E, and little r, where the minus pi little r squared, where little r is the radius of the hole, H-O-L-E. And this whole expression, which you could rewrite a couple of different ways, needs to get multiplied by the thickness. So imagine I have this. This is sine x and cosine x. Do you know that point of intersection? The place where sine of x equals cosine of x? This is in your warm-up the other day. So this is going to be pi over 4. We're going to need to know that. So we are going to find the region between sine of x and cosine of x. This purports to be a picture of that region. And we're going to revolve it around the x-axis to form a solid. We're going to write an expression for the volume. And I hope you can, well, let's draw it in. So I'm going to do what I do. I'm going to draw in the axis of revolution in red. I revolve around the x-axis. That's already shaded. I'm going to call it region R. Fly in the room again. And I'm going to imagine reflecting R over that axis of revolution. Doesn't have to be perfect. Looks like a Daniel Pearl shark, huh? All right, now I'm going to try to draw a slice. What's a slice going to look like here? I'm going to use green. Kind of wish I hadn't drawn the R after all. There we go. I'm just going to move that out of the way. Move the other R too, maybe. So I can see better what's about to happen. I'm going to use my green. I'm going to try to draw a slice. I'm going to draw a slice, and we're going to talk about what big R might be in this case and what little r might be. So I'm going to start at the axis of revolution with my green marker. I'm going to draw toward the curve that I know, and then back behind the axis of revolution. Okay, so that's a slice. For me, that's a slice of the whole, the big, the W-H-O-L-E. I'm going to do another slice. Do I have another green? Maybe I don't want to both green. Imagine a slice of the whole is going to start at the axis of revolution, draw towards sort of that inside boundary, and back up through. So I'm going to need to figure out the radius of the big green disk. I'm going to need to figure out the radius of the little green disk. So the radius of the big disk is my capital R. The radius of the little disk is my little r. I'm going to start my blue marker at the axis of revolution. I'm going to draw toward the edge of the big green circle. And then I'm going to ask myself, my blue radius I've drawn, I'm going to call this capital R. It's a vertical line segment, so to find its distance, I'm going to subtract the top y minus the bottom y. Well, what function did the top of my blue radius run into? Well, I have to know my trigonometric functions a little bit here. That top line is going to be cosine of x, right? Because cosine has the top of the hill at the place where x equals 0. It's going to be cosine of x minus, remember I started my blue line on the axis of revolution. That's the place where y equals 0. So cosine x minus 0, obviously I could just write cosine x. If I try to draw in the radius of the little green circle, I'm going to call this little r. Again, I have a vertical line segment. I'm going to subtract top y minus bottom y. The top of that little green circle bumped into the, whatever the bottom curve of that region is. I think that's sine of x. So it's going to be sine of x. Again, I can write minus 0. So I'm going to write an expression for the volume of this solid that I would get. And if I took a slice, every slice is going to have a hole in it. So one other way to think about this, imagine I'm going to have to integrate pi r squared minus pi r squared all times thickness. So I can sort of distribute the thickness, and then I'm going to have a subtraction problem. I can subtract against make two integrals. So I find that that tends to be the easiest for students to understand. Is really what I'm going to write is I'm going to write pi capital R squared d dx in this case. I had a horizontal axis of revolution, so I'm going to take vertical slices, and the thickness of every slice is a dx. So what this to me represents is, pretend you could fill in all the hole. This would be the volume of the WHOLE, and I'm going to subtract out the volume of the HOLE, hole, little r squared dx. So again, you could rewrite this so it's one integral. It looks more like this expression. It's not a big deal. Any correct expression is going to get full credit. So I'm going to write this now, pi times, if I'm writing an x integral, I'm going to need to use x limits. Remember we talked about what that x coordinate is, the place where sine and cosine bump into each other for the first time. That's pi over 4. So I'm going to integrate from 0 to pi over 4. Capital R squared dx, and capital R was cosine of x. Obviously I can write cosine of x minus 0, same result, minus pi integral from my whole my HOLE is going to have the same x limits as my WHOLE. Why does those words, why did they have to be homonyms? Pi over 4. And this is going to be little r squared dx. And little r in this case is sine of x. This is my expression for the volume of that solid. All right, this one came from your book? I guess it didn't come from your book. But it's nice because I have this picture that already has this green slice drawn in. So we're going to find now, we have a different region, the region in between y equals x squared, a parabola, and y equals 2x, a line. And we're going to revolve that around the y-axis. So we're going to see how this changes the situation when I revolve around the y-axis. But you can see how this this shape, this region, it looks like a, like a bird wing or something. It's not flush, it's not like tight up against the y-axis. So when I revolve it around, if I take a slice out of the middle, I'm going to have a hole in the middle of my slice. So I'm going to have to use what we would call the washer method. So I'm going to have pi capital R squared times the thickness minus pi little r squared times the thickness, where capital R is the radius from, very quickly, and then I'll draw it in officially, the axis of revolution to the outside of the solid, and little r is from the axis of revolution to the inside. That was hard to see. There you go, to the inside. So like the radius of the hole, the radius of the HOLE. Okay, so let's try this out. I have my axis of revolution is going to be here. This is nice because it already came with a picture. And then I can see here's the reflection over there. So, and then this green disc is already drawn in for me, which is nice. I need to figure out an expression for the radius of the big, like the outside slice. So if I have this is vertical. If I have a vertical axis of revolution, I'm going to take horizontal slices, and the thickness of the slice is a small change in y. We'll be writing a y integral, which means lots of things. Y limits. I'm going to make sure I write my radii in terms of y. And so, but what helps me get that right is, look at this. I have a horizontal line segment. My blue radius is horizontal. This is going to be capital R. How do you find the distance of a horizontal line segment? You need to subtract right x minus left x. So the left-hand edge of my blue radius ran into this function, y equals x squared, but I don't need an expression for x squared, I need an expression for x. So I have to take that equation, I'm going to rewrite it so that x is isolated. So I'm going to take the square root of both sides. The square root of y equals x. And that's the rightmost side, the square root of y. Minus, and then where did I start my pen? I started it on the axis of revolution, which was the y-axis, which is the place where x equals 0. So obviously square root of y minus 0, I could just write square root of y. For little r, I'm going to start my radius at the axis of revolution and draw toward, whoops, I drew too far. This is hard to gauge. Okay, well, the line I bumped into was y equals 2x, which is actually a line, so that's good that I said line. Y equals 2x, but I don't need an expression for 2x, I need an expression for x, so I'm going to re-solve that equation for x and get y over 2 equals x. Again, this blue radius is horizontal. I'm going to subtract right x minus left x. Right x is y, that's a y. Y over 2. Minus the left x, that's where I started, and my axis of revolution was the place where x equals 0. So I'm going to again have a minus 0. This is just y over 2. Now I have an expression for both of my radii. I can write a formula for the volume of a washer. It's going, and I know my radii are all in terms of y. I decided the thickness of my slice is going to be a dy. I'm going to write y integrals. What are my y limits? The lowest y in this picture is at y equals 0. The highest up y, I can tell from the picture, but notice I might have to figure it out on my own by setting these both equal to each other. I'm going to get 2x equals x squared. I'll figure out x equals 2, but that tells me that y has to equal 4. So my formula for washer is pi times the integral from 0 to 4 of capital R squared dy, and my capital R was radical y, minus pi times the integral from 0 to 4 of little r squared dy. Little r in this case we said was y over 2. Notice this expression would not be too difficult to evaluate. This is going to be pi times the integral from 0 to 4 of y dy, minus pi times the integral from 0 to 4 of y squared over 4 dy. Both of those antiderivatives would be relatively straightforward to find, and you could evaluate this one by hand. I'll leave that as an exercise for you.